task to put a man on the moon in the summer of 1969. What not many people know is that we need to thank a lady, Margaret Hamilton, who actually directed the group of people writing these 60,000 lines of code. I will not go through the details of what the code does, but you see there is a part on the left which is in assembly. I mean, for us, we are computer scientists, we love this part, surely. But there is a part on the right, I mean, these comments written in plain English that allow us to understand what the program does even more than 50 years later, even if you don't have the documentation. And you see, this is a message to the human, not to the machines. The comment do not go to the execution of the machine. You can say, okay, but this is because it was a very difficult programming language in assembly code, that's the reason why you have comments. Well, not really. Fast forward, no, this is too small. I mean, fast forward a few years up to the COVID crisis. This is a small excerpt of COVID sim. It was the software that was used to simulate the spread of COVID written by a biologist in England. And you see the amount of comments that are here. Everything is commented in the program, even if it is using a modern programming language, because you need to understand what is going on. Then if you want to know the story, I mean, this software is open source, was put online, and then you had some very brilliant programmers, in particular John Carmack, who was the author, he was working with IT software, if you remember, Quake 3, Quake Arena, all the ancestors of Call of Duty. I mean, this brilliant programmer spent some time to actually rewrite this, because this was not written by a computer scientist. There were a lot of stuff which was not correct. But the simulation was correct. Okay? The simulation was correct. And so the reason why I'm showing all this is that this was written in a nice article in 2006 by Ben Schuster, who was the board director of the Computer History Museum. The source code is really precious. It is something that allows us to open a window in the mind of the designer of the software. If you only have the binary, of course you can run it and play the game or put a like on the page of the file. But you are missing all the understanding of what is going on, and you are not able to modify to make it evolve. Well, now, the point is that if you look at source code, I mean, in the last 30 years, open source has taken the world by storm. You have open source all over the place. Now, using Software Azure, that you will discover in a few minutes, we did a study over 50 years to see where this software comes from. I mean, what you do, you look at the email of the people that actually make a modification. You look at the time of the day where the modification is done. Okay, so and you try to attribute this to a particular geographical location. Of course, these are heuristics. It's not necessarily super correct. But approximately, you see, at the beginning, you had a lot of people working on computing in the US, in Europe, etc. But if you look at the trend, now in the last years, over a third of the software developed worldwide doesn't come from the US and doesn't come from Europe. So this is really a global undertaking. Not only is a global undertaking, but we also have seen that the way programming languages evolve over time is significant. So we have seen C programming language in the 70s, 80s a lot. And so at the beginning, this is a percentage. So this table shows you over 25 years the evolution of the percentage of use of a particular programming language. So of course, in 2000, there were much less software than in 2021. But the percentage, you see, at the beginning, almost half was in C. Now C is a minimal part of the activity because people are using other programming languages. And also to build this picture, we used in a crucial way the software heritage infrastructure. We'll come back to it. Last but not least, here is another diagram that shows you the evolution of original content that is produced by programmer over time. You see these lines, so the red line is the file contents, and the blue line are the revisions, that is the commits that you make on a repository. And you see that basically on over 20 years, the trend is very stable, and this is a linear logarithmic scale. So basically, the number of original contents is exploding. It doubles every 2 years, systematically since 2000. So it shows you that there is a lot of software coming out. It's also a challenge for us because we need to archive it, and if it happens every 2 years, it's kind of a challenge. But you see, we are now faced with an incredible amount of open source, written in a variety of programming languages, written all over the planet by different people. This is precious knowledge. I mean, this is precious technical and scientific knowledge. And so, as we have seen during COVID-19, I mean, this is was an article on the New York Times by this guy who wrote a book called Sapiens, and it was very popular years ago. So we were saying the real antidote to epidemic, but you can say to any challenge for humankind, is actually to build scientific knowledge, what we are all trying to do together here, and to actually to share and to cooperate at the global scale. I know that today, if you look at the geopolitics, this phrase sounds a little bit less realistic than what we knew a couple of years ago, okay? But let's try anyway. And the other important point is that software powers all fields of modern research. So these are numbers that we finally managed to get 3 years ago. And let me explain. So when you go and talk to other people in other disciplines, and you ask them, is software important for you? Imagine you talk to somebody in the social sciences, or somebody in geography, or linguistics, or law. Okay? Do they know how much software is important for them, how much software is produced by them? Probably not. But in France, we have a National Committee for Open Science, which was created in 2018, and part of this committee, and we wanted to have a monitor to see the amount of open science produced. So, of course, there is an indicator that shows how many papers are available as open access, and this should go up, I mean, to make the politician happy. But then we added also an indicator on software. How does this work? There is a group at the Ministry of Research that actually takes all the publication by French authors, uses a machine learning model to detect in these publications all the software mentions. So, for example, if I say, I have used Python to write the tool foo, which is available there, I have used Python, this is a use of Python, to create the tool, this is creation, which is available there, this is sharing. So we track creation and sharing of software. These are official numbers that you can find, again, I will share the slide. Everything in blue is a link. You click on the blue thing that you get the supporting material. Okay? I do not like to just give opinions. I'm still a scientist, so I prefer to give you pointers. And so this shows that in all disciplines, from social sciences to life sciences, software is all over the place. So that's the reason why it is super important to keep it. And the other important part is that, as Donald was saying, I mean, we are still in a position to talk to the original creator of this software. You know, our friends in physics would like to be able to talk to Newton. Too late. Okay? In mathematics, you would like to go and talk to Leibniz or other people. Too late. But in computer science, we can still talk to the people who invented the discipline, created the original thing, and we need to collect these stories. Okay? So, if you really want to do all this, I mean, preserve the knowledge, collect the knowledge, make it useful, we need an infrastructure dedicated to this mission. And the point is that this need has become more and more evident over time. If you look at what happens in academia, for example, I do not know how much you follow this kind of issue. 2011, in the life sciences, people started noticing a crisis in science. So you have papers that say 2 + 2 is 5, others that say 2 + 2 is 22. This is not really science. I mean, how can you reproduce a result? So you have issues with reproducibility results. Even in Jupyter notebooks, if you find them, and there are some software engineering studies that show that most of them are not reusable. mean, you rerun the thing, you don't get the same result. I don't just counting. And in industry, in other world, a few years ago, we started getting this big issue like the Log4j, Log-shell vulnerability. I mean, that spread all over the world. And so now you have regulations and I mean, all the politicians are worried about cybersecurity vulnerability, which was not the case many years ago. There are regulations in Europe. The Cyber Resilience Act was voted just a couple of months ago. And there are regulations in the US also in this direction that makes cybersecurity even more important. And so we had awareness, which is raising. And this is the point because I'm taking too much time. So I will not show you all the slides which are here. To address these issues, 10 years ago, we created an initiative which is called Software Heritage. The mission is precisely to go out, collect every single line of code which is publicly available all over the planet, preserve it, making sure it doesn't go away, and make it easy to find it and reuse it. Okay? Collect, preserve, organize, share. These are the keywords in what we try to do. So in a nutshell, this would be building a reference catalog of all the software which is out there. Most of you are using GitHub, I suppose, but other people are using either GitHub.com or local instances of GitHub. We do it a lot in France. But there, you know, there are thousands and thousands of different code hosting platforms around the planet. So there is not a single place where you can find an index of everything which is available out there. But this index is being built inside Software Heritage today. But it is not just a catalog, it is also an archive, so we make sure the software do not disappear. You know, when I started computer science, you know, typical young sciences, we were thinking, I mean, what is losing data? Impossible. I mean, the digital data, you just make a copy, you cannot lose it. Well, not really, right? And in particular, now you know, you have a 256 gigabyte USB key, fantastic. You lose it, you have lost 256 gigabytes of data. I mean, so it's not an easy thing. And actually, in 2015, here, Google Code was a platform used for doing collaborative project development. There were 700,000 projects there. It was unplugged for business reasons. Gitorious, another platform. 120,000 projects, unplugged, in 3 weeks. Actually, there was code of mine in there, okay? So, and I remember I got the message in March 2015, very American message to say, great news. Great news. Also, I had won the lottery ticket, but no. The great news was that the owner of Gitorious.org sold the company to the owner of GitLab. So the great news was for him because he is getting a Ferrari. Okay, for me it was very bad news because at the end of the message he was saying, you know, now it doesn't really make a lot of sense to keep two infrastructure apps. So starting from now, you have 3 weeks to take your stuff and go away because we are going to unplug the servers. You see? So this is not just the forge is a place where you put the project, you can remove it. Sometimes the forge goes away with hundreds of thousands of projects. I mean, so having an archive is fundamental. And so for people doing open science and reproducibility here and in other places that believe that just putting a project on GitHub is enough, think again. GitHub is not an archive. Okay? That you can change the content. The content can be taken down, in particular regulation today, or the forge can disappear. So, and then last but not least, we are building a research infrastructure, that is to say a tool to explore the large galaxy of software development over time. There are hundreds of millions of projects, tens of millions of developers working on software all over the planet for decades. We do not have a tool to explore this variety of software development, and we would like to have it. I have friends in astrophysics. They can federate and build incredible telescopes like the James Webb Space Telescope. 30 years, $10 billion to build it. We must do the same. in computing, building such an infrastructure to explore the software. And there is no lack of reasons. Because now everybody's scared about cybersecurity. Well, okay, so let's build an infrastructure that covers all the components of software worldwide, and trace vulnerability, highlights problems here and there. I mean, we should be doing it. So how is software actually designed? It is designed as a common infrastructure, one open, common, non-profit, shared, open source infrastructure that has exactly this mission, collect, preserve, and share. And then we try to address the needs of a lot of verticals, so the cultural heritage, revealing the history of computing, industry, license compliance, vulnerabilities, security, provenance of software, etc. In research, the place where you store your software, and a tool to analyze the evolution of software. For public administration, a place where you can put software which is built on public money, and where you can share metadata and information about the software that different administration use over the planet. This is today the largest public archive ever built of software source code. The numbers are not up to date because they change every day, so you can go to softwareedge.org to see the current numbers, but it is more than 350 million projects already archived. They break down to more than 22 billion unique source code files. Why are they unique? It's all because actually, you will see in a few slides, we identify each file content with a cryptographic hash, so it's the same file content is in different projects, we notice it, and we store it only once. And you see over 86 million different contributors that you can identify in this history of computing. Where does all this come from? I mean, of course, GitHub is the biggest fish in the pond today, but you also have GitLab.com and all the variants of GitHub installed, but Bitbucket, but Segit, but NPM, but PyPy, etc. Debian, Fedora, Ubuntu. So you have a code hosting platform, package managers, distribution, all of this, which is archived. This is supported by UNESCO and many other organizations that share the vision, and actually it's supported in terms of money, by Inria, who supported us in the starting of this in 2014, and many other companies and organizations and governments, etc., that try to help us move forward to foot the bill, because we need to have machines, we need to have engineers. I mean, you do not build such a thing in an afternoon or in a garage. Okay, so we need to have people working there. How does software heritage work? Well, over 10 years, we built a giant crawler of source code origins. So we built adapters to talk to the GitHub API event feed. So I'm talking to GitHub and say, can you tell me all the projects that you have today? Sure, here they are. Then I go to GitLab and say, can you tell me all the projects that you are hosting today? Sure, here they are. The bad news is that there are not two equal APIs. So we need to build an adapter for every single different technology. So we develop tens and tens of adapters over time for all of these kind of things. And now we have this list, 350 million origins, and just a list. Now we need to get the software from there. Bad news number two, not only there is no standard for the API event feed for the repository, but there is no standard for maintaining the version control system of the software. Today you are using Git, most of you. When I was young, I was using the old system that basically said, this is a file that works.c. This really works, .c. Final version of the project.c, remember that kind of thing? Okay. Now then RCS, then CDS, then subversion, then Bazaar, Mercurial, Git. Since we need to archive all of these things, I cannot just say, I will just archive GitHub. No, we needed to build adapters for every single one of these tens and tens and tens of systems for packages, etc. And we did this because we were forward-looking, so we are saying, we build an archive for the long term. I want you to be able to read the archive in 10 years. If I only keep a copy of the Git repository, Maybe in 10 years, the version of Git is no longer the same, we are not able to read it anymore. So we decided to go the extra mile, make a big effort to build adapters that reread the history of Git. They read the history of Subversion, or the history of CBS or RCS or Mercurial, etc. They reopen all the packages that are coming outside and embed all this in a giant, deduplicated, direct acyclic graph that gives all the history of software development across the planet in the last 70 years. The data structure is super easy, so you only have, well, super easy, definition may be a little bit complicated, but I mean, basically, the type that you have is a file content, a directory, a revision, a release, a snapshot, and an origin. So the origin is typically the URL of the platform where you download something, or if it is a Debian package, we have a namespace like that, call or something. But this is uniform, it does not depend at all on the original forges or the version control system. It is completely unified. This means that you have, in this graph, 50 billion nodes. The nodes are the file content, the revision, the directory, etc. 800 billion edges. An edge is something that is telling you inside this directory, this file content is called the foo. Or this directory inside this revision is called bar. Okay? And completely unified. If you want to know the size of this stuff, I mean, all the objects, the bits of the graph, I mean, the file contents are almost 2 petabytes. But remember, this double every 2 years. Okay, so in 2 years will be 4. If we, unless Gen AI will actually increase the speed of growth of the source code. But the graph is not so big, it's a few dozens of terabytes, and we can use it in an intelligent way. Each of the nodes is identified by a particular cryptographic identifier. These are called the software hash identifier. It is now a standard, an ISO standard. It took us almost 4 years to get here. But it is an ISO standard, that's how to do it. And so on the content, or on any node of the graph, you find one of these things. The prefix SWH says this is software hash. There is a version for the kind of algorithm used for doing the hashing. A tag that says what is the object you are identifying, so the content, the directory, the revision, the release, the snapshot. And then, look, if you want to compute the hash of the file, it's easy. You type the shell one sum of the file. If you want to compute the hash of the directory, or the revision, or the snapshot, then you need to agree very precisely on how you export the hashes from the lower level to the higher level. This is why we had to write down the details in something which is today an ISO standard. We also add some extra, this is not very real, but we add some extra qualifiers that allows you to say what was the origin where I found this object, what was the status of the repository when I visited the retrieve. If I had looked in a particular file content here, it was called this name inside this directory, which is the root directory of this particular revision, and you can also point to lines inside the code. So, for example, the example that I have shown you, the Apollo 11 source code excerpt, you have seen in the first slide. When you download this slide, you click on this blue link. Behind this blue link, there is exactly this, this thing, and you will go and you will find yourself on the archive exactly in front of the object. Actually, we can try to do it. Let's see if it works. So you click on this, and here you end up in the archive in front of exactly the fragment of code which was interesting for you. And you find it in the right context. See, you say, as this particular file is present in many places, but here I'm telling you, this is a file as it was seen on GitHub in this particular repository in the last snapshot that we took on March 26, and inside this particular revision. Okay, so you have all the information to identify exactly the fragment of code inside the gigantic graph that you are using. This is actually, this is, for me, it was something I wanted to have for ages when I was writing my papers, for example. I wanted to show an example of an algorithm that was taken from the implementation, which was attached to the paper. But you know, you have page limits in the presentation, you do not have the time to put everything. So I was very frustrated not to be able to show where we can go. Now I write the article in a different way. So I make a simplified version of the code, and in the caption I say, this is a simplified version of, and then I have a link like this one that brings me exactly in front of the thing. Maybe as a small break in the presentation, let's look at what is going on here on the archive. So here, this is a software edge archive. You see, very simple, you have a search bar that allows you to search among the projects that have been archived in there. For the moment, this is not a full text search. It is a search on the URLs of the origins. And so I always use my project as an example because I know it well. So you see, this is my project. We find it on Git, but also on a particular release and other places. When I arrive on my project, you see this is not an archive. I mean, the usual archive is a place where you have a zip file that you download. No. Here, the software archive is designed by developers for developers. So you can navigate inside of the archive like if it was a Forge, okay, a hosting platform. You can go inside the source code, for example, here. Let's take this part. See, this is my code written in the code in 2012. If you're curious, this was a very simple implementation of a MapReduce algorithm multi-core on a machine, written in very few lines of code. We were very proud of writing something very compactly using some click on the Linux kernel downstairs. And we had a paper publishing this. And then the core of the algorithm actually is, let me get to the right place. The core of the algorithm is here, you see, from here to there. This is exactly the fragment of the core algorithm. Now what I can do is I pull out the red tab. This red tab is there all over all the time. And when you visit the archive, you see something you're interested in, you pull out the red tab, and you can copy the identifier and put the identifier in your article, or in a bug tracker, or in a vulnerability issue, or in a contract with a company. Okay? And now you know exactly what this is talking about, and you're sure you will find it in 2 years, or in 2 minutes, and 2 hours, like a traditional project. Not only, I mean, just a few weeks ago, we created something else. We added the possibility, this is typically for us in the research world, we added the possibility to automatically get a citation. So I can pull out this tab, and now you have the big text fragment that allows you to cite exactly the part of the thing that you are seeing. Since here I'm seeing a fragment of code, the big text entry is code fragment. Okay? If I'm looking at software globally, then the entry is software. But now you can use it to tell people how to cite your software, you can use it to cite the software of somebody else. And this is agnostic of the platform. Doesn't matter if your code is on GitHub, Bitbucket, on your institutional platform, whatever. As soon as it is archived, you get this functionality automatically. And so the simple example I have given you, that you say selecting a fragment and sharing it with somebody else. This seems trivial because we are used to do the same thing using modern code hosting platform. But remember, the modern code hosting platforms are not archives. And some of them have this functionality, some of them don't have this functionality. The particularity of software heritage is that one, it is an archive. So a piece of software which is in there will stay there, so you will not have property. Second, it is not bound to any particular code hosting platform. The identifier we produce are the same. Doesn't matter if you're using Git or Mercurial or Bazaar or the packet manager or whatever. So, same identifier schema and universal archive. This is a game changer with respect to using the similar functionality on current platform. And the same for citation. Now, to continue a little bit, I mean, you may ask us, but okay, how often do we archive all this content? Well, we had a crawler, of course, but we do not have the resources of Google. So, for example, we may lag behind a few months, in particular on GitHub, which is growing. You know, GitHub is growing by 50 million projects every semester. So we have the information. It's huge. So what we have is the possibility for you to go here to this thing which is called the Save Code Now functionality. So here you can pick one of the supported action control systems, Bazaar, CVS, Git, Mercurial Subversion, for example, and say, I would like you to go and archive for me right now this project which is on GitHub. Then you click on Submit. Okay, now it is put in the Save queue. It was pretty fast. I mean, already succeeded. You see something. This has been archived immediately on request for us. Since we opened this functionality, there have been almost 2 million requests to do the archival. The other thing that we have added is the possibility of configuring a webhook on your platform. Actually, what we support, GitHub, GitLab, Git, Bitbucket, and SourceForge. You can set up a webhook there to say every time I make a commit, or every time I make a release, every time I whatever event, trigger an archival, and this is what is happening on the other side. Then we added another functionality, the possibility for you to ask us to archive not just one project, but to call another full forge. So imagine you have a forge here in your institute for software you want it to be archived regularly, but you create an account because we need to know who you are. That you send a request for archival, it comes into a list of things and will be incorporated in the archival loop regularly. So this gives you a little bit of an idea what is going on behind this. Now, this was part of my demo thing. Now back to the presentation. How many minutes I have left? Just because I forgot to start.
That you want.
I'm asking because it is very dangerous. I have a tendency to speak a lot. So when I speak it too much, you just throw tomatoes or do something. So I know. So when we started doing this, we were just motivated by the fact that we wanted to make sure this software, which is a precious part of our human knowledge. Actually, this is one of the reasons we had a partnership with UNESCO. When we started this setup, UNESCO should be interested in this. And actually, yes, they were interested because UNESCO is a United Nations educational, scientific, and cultural organization. There is education, there is science, there is culture, and all the 3 dimensions are in this infrastructure, so we are working together. What we didn't know, that we were building a revolutionary infrastructure for many other applications. Because the original motivation was a kind of a library of Alexandria, okay? So a library of Alexandria was the code. And if you remember how the library of Alexandria worked back then, it was a place where the emperor had copies of all the important documents that were found by the savvy people he was sending around the world. So I sent somebody to the library in Rome, I copied the papyrus and bring it back. So you have in the library of Alexandria absolutely everything. Very similar to what we do. Okay, so you pull and get copies. You also know that the library of Alexandria burned up at some moment in time, no? It disappeared. So we are very wary of this, and this is the reason why we have several copies, 3 copies of the data under our own control. And we started a few years ago a mirror program. The idea of the mirror, it is a copy but not maintained by us. Okay? Because if I am hacked and I have a copy, 3 copies, maybe the 3 copy will also disappear. And so if the hacker is intelligent enough, he will find out or she will find out the password. But if you had a mirror maintained by another organization with another technology, and this mirror is only reads from us, but we cannot write into the mirror, hacking it is more difficult. Okay, so we are setting up a mirror network. But the point is that we found out that at the end, this is actually much more than the Library of Alexandria. First of all, as you have seen, this is not just an archive, it's much more. We keep all the graph of software development, not any graph, a marked graph, a cryptographic graph. So technically, this is a blockchain for software. Okay. If you remember cryptocurrencies, etc., the blockchain is a chain of blocks linked by cryptography. Then when people talk about blockchain, they usually add another thing, which is a consensus algorithm to maintain the ledger without a central node. So we do not have the consensus algorithm, but all the rest is there. Okay, so it's a blockchain. Then it is an incredible tool for actually archiving and referencing the source code, which is used in paper and presentations. And since we did this enormous amount of work in removing the details, the non-interesting details of the platform from where we get the software, we actually did the work that you usually do in machine learning when you do data cleaning and data normalization. So the data which is in the archive is already ready for you for doing a tons of different analysis. So there are too many things to say. So I will try to jump in, and if you have questions, please ask. For example, this was a demo time, so I already did some of the demo, but then you will have this kind of slide, and every single blue line brings you to one or the other particular functionality that you can see directly. So I give this exercise to the reader, and then this is getting adopted in science. For example, if you see, in France, we have a national plan for open science where all researchers get the recommendation that they produce software to archive it in software heritage, to make it available for them, and to reference it in a national portal, which is called HAL, which is a national portal. That has some functionality. Maybe I will take 2 minutes to show you, but anyway. Then this is part of the French National Strategy of Research Infrastructure. At the European level, it is recognized as the foundation layer for connecting software with the publications and other things. If you look at some results here, this was a lady for the life science digital analysis of the kind of reference used to point to software inside the publications. And she found the software was the 3rd most used identifier. In the computer graphics, they had an initiative to actually check whether a software does what it says it does, and then you get a stamp. But you don't know which version was the right one. Now they added in archival and software ledger directly to know this version here to make sure it will stay there. But so let me skip the demo for a moment, and all this, I hope you find this interesting. They say, what is the science now? Where we are looking for science and research, what can we do? Now, the interesting point is that on top of building the archive, we wanted to make it easy for researchers and scientists to actually do something interesting on top of this data. So we decided to make available regularly. At the beginning, it was once every year, then once every 6 months. We try to increase the frequency. A full dump of this big graph that is easily available to you for free for doing research on top of it. And here I have a simple example to show you. For example, you see before the example, this is where you can find the data sets. One of the data sets is stored on the AWS in the open data platform. So you go to Registry of the Data AWS software heritage, you get all the information on this page here. And in particular, if you want to download the graph, the structure of the graph, not the 2 petabytes of the contents, just the graph for doing analysis on the graph. This is in ORC files, the columnar storage of the files. And you download it from here, you do not do not even need an account on Amazon to download this stuff. Took some time to negotiate with them to get this, but I mean, at the end we did it. And what can you do with the graph? Now, let me tell you a story. So, many years ago, I have seen a paper published in the software engineering community where the people were trying to study how developers behave. And the question they were trying to answer was, what is the most popular commit verb used by developers? What does it mean? I mean, when you do a development and you commit the version, you have a log message that you put in there. And the good practice in development is that this log message should start with the verb. Because you should read the commit as this commit will, and then you have a verb, for example, fix this mistake. Or this commit will remove that file. And I'm not sure this is super interesting, but they wanted to do this. And so the paper said, okay, we bought the machine, we downloaded 150,000 projects from GitHub, we hired 2 postdocs, and we spent a lot of time to collect the data, download the structures, etc., perform this paper, and at the end we got this result on 150,000 projects. Now that we have the software heritage, can we try to do the same? Yeah, let's try. Okay. So instead of the slide, this is dangerous, but we'll try to do it live. So here I am connected on the AWS console, our account on AWS. In AWS, this is Amazon Athena. Amazon Athena is a SQL query engine, distributed SQL query engine that is Amazon implementation of an open source software which is called Presto. And so here you see, this is our thing, okay? We can load directly one of the dumps of the graph that are available in S3. Now I'm taking the version which was created on December 6, 2024. And I can ask this question. I don't know if you can read it. So I'm saying I select from the revision table the message field, only the message field that are smaller than 1 megabyte. Sounds strange, right? The people are committing things with 60 megabytes of commit message. What the hell are they doing? Sometimes you find a data set in the commit message. You say, this is the data we use. Anyway, so less than 1 million messages into the transcript. And then you do some, you convert from PDF, you trim it, you remove space before and after, then you split according to space, take the first part, then put it lowercase and get the step to simplify. And then you count the number of occurrences, you drop the words which are empty, group by word, order in descending order, and take the first 20 ones. And you say, Roberto, what are you doing? Because if it took 18 months for the people to do this computation, we do not have the time to do it now, right? Well, now we are running the query live, so you see I'm not cheating. So this is scanning the revision table, which is part of the dump of the graph. And by the way, the economic model behind Amazon Athena is that you pay only for the amount of data that you scan. You do not pay for the compute. And the price, last time I checked, is $5 per terabyte scanned. Okay, so we can see how much I am spending to give this demo. We are a bit more than a coffee for the moment, in 145 gigabytes, 150. It's finished. 44 seconds, a little bit more than a coffee. And here is the result. I mean, 500 million commit messages start with update. Then you have 250 million messages start with merge, then add, fix, etc. Well, okay. I'm not going to publish a paper with this, okay, the people already published it, but it gives you an idea of the power that we have now in performing analysis at this scale on this kind of infrastructure. This was totally impossible before. And so the idea for us is also to make it possible for you to study what happens on this, on the Galaxy software development without having to implement complicated pipelines to go and fetch and recover data all over and over again. But this is interesting. So in this slide, you will see a bunch of more information on how to get it, and in particular this thing. The request is that this was on a slide, in all the slides, this was on the previous sample, the graph was smaller, so that the numbers are not the same. And, but, I mean, if you study databases properly, you know that, I mean, SQL is fine for tabular data like this, but if you need to traverse a graph, usually it doesn't work very well. So we had to spend time to find a way to make it possible for you to perform sophisticated analysis on top of all the graph software without calling SQL queries over the time. And this was done by a certain number of persons. Antoine Pietrich was a PhD student with us, and he moved to Google after. Let's say Google picked him to get the technology, and then Stefano and Sebastiano and Paolo worked together on adapting a technology that was developed for the web, a framework which is called Web Graph, that compresses the graph for the web used by people like Google, Microsoft, etc. It has been adapted to work on the software heritage graph, and the result is that today, I mean, the slides are not up to date now, it is 400 gigabytes that you need, and this is 50, and this is 800. All the structure of the graph fits in central memory in less than 400 gigabytes. So a machine with 400 gigabytes, actually a machine with 1 terabyte, today is a little bit less than 10,000 euros in France. Okay. So for a department, you probably already have a machine like this. And here, the traversal time is a few tens of nanoseconds per edge. So you can perform incredible analysis. I had a tons of demos here. I will give you the slide for this. But I just wanted to conclude with one thing, which is an example of how this is changing the way people are doing empirical software engineering studies. And now I'm switching to slides which are not mine. These are slides from a colleague. That's me. These people, I mean, this is Benoît Condemare, which is a research team at Inria. These people are interested in doing sophisticated analysis of the Android system applications, etc., etc. But the starting point for this analysis for them is how can we find all the Android applications to perform analysis of their source code. And so there are two possibilities. One is building tools that go and call GitHub, and etc., different API to try to get what is interesting, or just go to software and find a thing there. And here you will see how you can use the two things. One is SQL, and the other is a graph, to prepare the data for their analysis. So what they do, they want to find the applications that are Android. I mean, all applications that are applications for Android, they have a special file that is called Android manifest.xml. So what do? First, you make an SQL query on the directory table to look at all the files which are called android.xml. You identify every single one of them. Okay? So And this you can do it with the SQL query. Then you get the identifiers, and so you know what are the blocks. And not find the block, I need to find the origin, the place where the application is. And to do this, this is a full traversal of the graph, so you will not do it using SQL. What they do, they use the graph I showed to you to find up to traverse the graph go there up there. And so this is done in less than a day. Everything is immediately done this way. And then they start doing their own research, which is where your value added is, not downloading things all the time. So to finish, for this kind of studies, using some project, first of all, we are not just using GitHub, you have a much broader system. You have a standard format, no need to do spatial handling or Git subversion, etc. You can make your research reproducible by just saying, we did our research using these files, and we just publish the software hash release. No need to republish all the data because it is already in the archive. Okay. And actually, we are already doing all the heavy lifting for you when you do research. Now, to finish, sorry. And this is another thing, cybersecurity, AI, I do not have time to go there. Who is behind all this? This is not just me. I mean, this is a project that was started with Inria, that since day one, we wanted this to be something which is worldwide. Okay? With a lot of people coming from different places. The image is not very clear. I mean, this is a current team. We are more or less 20 people. We lost the friend, unfortunately, to a cancer last year. But we have 20 people here. This picture is a picture of the community at UNESCO last year, where we were having this meeting. We had a series of ambassadors, I mean, people that know about the project, talk about the project, and going around. There are more or less 30, 35 people even. I remember a couple of Brazilians, by the way, and you can have a look in here. And the last news, we are part of the work where we try to connect publication with research. We worked on AI, so the stakeholder 2 model built by Hugging Face service now in Inria has been trained on the software heritage archive. There is a full project dedicated to cybersecurity, vulnerabilities, etc. There are projects on academia to integrate software with Zenodo, integrate software with other things like this. And we started recently a project where Patrick is an advisor for building something even bigger around software heritage. The project is called Code Commons, to enrich software heritage, to provide groundbreaking tools to select data sets for machine learning training and for being able to identify whether something that the model produces is or not similar to something which is in the archive, to provide attribution and provenance of the content. If you want to know more, the 2024 annual report is out. You can get an overview of what this project does. And sorry, we skip this. So if I can conclude with a word, I hope you can see that we are really trying to work to make it complete a grand vision. What is our grand vision? I mean, software has changed our world, is changing our world. Software as code is a core of the software which is changing our world. It is so important. The software is of good quality, that it is well maintained, that it is reused properly, etc. So we need to bring together academia, industry, public powers, etc., to build a better technology for the future. So if we want to do this, I mean, we need to work together. So software is a starting block. Okay? It's vendor neutral, it's not a company, it's not a profit, it's a foundation. It is open source, it is already worldwide, it's designed to be long term. So the joke with my friends is that I will never get a Ferrari out of software. Because you know what they did in my team? Last December, in December 19th, on my anniversary, I was just there in a meeting with the team. Then one of them took out a little box and said, and this is for you. I literally, it was a model Ferrari. Because I say now you cannot say any longer that you cannot have a Ferrari working on software edge because you didn't specify the size. Okay, typical geek joke, okay, this kind of thing. But, well, there are already so many things that you can do. I gave you a short overview of what you can do this kind of thing, and but we need more. We need more. And here you can help. I mean, everybody can help. You can use it. You can disseminate it, you can do research on top of it, you can contribute to the challenges in research. For example, you can think one of the challenges now in the new infrastructure, actually having a huge data model with tons of data with efficient queries, etc. for selecting subsets. This is a big technical and scientific challenges we need to tackle. But there are many, many more. So feel free to come in, we are open, no problem whatsoever. And sorry for being long, I'm sure I have been longer than expected. But thank you very much for your attention. If you have any question, I'll be more than happy to answer them. Thank you very much.
Any question?
First of all, I'd like to start by saying your work is very important and I appreciate it. But as a resilience, in a resilience perspective, did you consider a peer-to-peer solution for backups? Because even though you have a long-term plan and you intend on maintaining this project for years, we never know the future. So if something else happens, can somebody else take over the infrastructure and whatever you guys have set up to continue archiving and maintain whatever we already have collected?
Thanks a lot. Very, very nice question. And let me sum it up this way. Okay, so when you build an infrastructure like this one, and you want it to be resilient over time, you have basically at least two architectural choices you can make. One is to make the infrastructure totally distributed and then make it federated in some sense. And if you go into this direction, if you look at the work done on Web 3.0, on IPFS, the interplanetary file system, this kind of hash-based content distribution, etc., this is a way to go. The other architectural choice you can make is to say, no, I will do a centralized infrastructure, but replicated. Okay, the idea is always to be resilient. So many years ago, I met Juan Benet, who was the author of IPFS, before the cryptocurrency craziness, before he created the Filecoins crypto. And so we started looking into the possibility of using that technology, but the problem with distributed system like this is it has zero guarantee that the content is actually maintained over time. You know, DHT, the distributed hash table, okay, you can make 3 copies of everything, but if by chance, bad luck, the 3 machines having the 3 copies go down, you lost it, that content. So I was asking this. The result is that today we built a bridge between software heritage and IPFS. So you can we use it as a content distribution network, but we do not use it for long-term storage. So our choice for the moment has been to do this with a central node, several mirrors which are totally independent of us, and every single line of source code, everything is specific. There is not one line of proprietary code in all the infrastructure of software heritage. You can download it, install it, and run it yourself. There is a ton of documentation. It is not perfect, but I think for us it's the best chance for making this resilience. Eventually we all die in fire, but I hope not, in Paris with the machine. There are 4 mirrors in different countries in this moment that have the data. They are just mirrors, they do not have the coders. If you want the coders, you download it, install it, run them, and start. So this is why we made this particular choice. I hope this answers your question.
Yeah, of course. Thank you.
Yeah, my question was, at the beginning, did you always aim to archive everything? Or did you just start with GitHub and then branch it out? Because it must be a huge amount of work. And at any point, did you consider that you may not be able to archive everything?
Yep.
You're very right. I mean, there are two. I think there are two sub-questions in what you are asking. One which is not exactly what you said, but let me point to it, which is important. First is, do we really need to archive everything we can find? I mean, do you really want to archive a student project which is on GitHub, for example? Probably not. And when we started discussing, people actually do archiving professionally, I mean, libraries or national archives, etc. The first question they asked us is, how do you you have a curator? I said, what is a curator? A curator is a person that says whether yes or not this thing can be archived. I mean, if I go with my memories in a notebook to the Library of Congress, I'm not sure they will take it. Okay, so they have a filtering. We decided from the beginning not to filter anything, and there are two reasons. One is technical, the other is philosophical. Technically, with the technology you have seen, I mean, the duplication, mass duplication, etc., we do not have space for storing. So, but even if you have a space, maybe you don't want to archive everything. And then this is my old guy experience. I remember 1995, on the Usenet, I saw this message by a person, Rasmus Lerdorf, saying, I am fed up to modify my HTML page by hand every single day. So I came up with a little hack, my personal home page tools, that you can use it. It is free, do whatever you want. Personal home page tools, PHP, which is unfortunately still the most used technology for building website in the planet. So if we had decided back then that this was just a minor thing, we would not have the history. So we want to have everything. But then going back again to your very original question, yes, at the beginning we started with GitHub because it was the biggest one, and since we had to build one adapter for every technology, we started with the biggest one when you put this together. But then we really put the point of honor to actually be able to collect everything. And a few years ago, we managed to get the grant from the Sloan Foundation in the US, not for us, but for funding other experts or companies or developers or contributors to build adapters for other things, for other things, for Mercurial, for Subversion, for other things like this. And so slowly over time, we try to actually get everything. And not only, it is software edge, not free software edge. So we really want to have everything, in the end, unless Disney manages to change again the law on copyright, after 70 years, everything goes into public domain. Okay, so everything we can get eventually will be open and will be able to be archived, but we really try to get everything, including something which is not interesting. There is a selection on interesting, not interesting, we come later and not before.
I think my question runs on the same line as the previous is, do you have any specific methods to remove redundancy?
Yeah.
I know you spoke of the hashing, but some codes fundamentally have the same properties, but different characters, so they generate different hashes.
Yeah, sure, absolutely. Another very good point. So when we started the project, again, remember, we started very small. At the beginning, I was alone, and in the first 2 years, we were 4 people, so it's not a lot for doing this. So we had this idea of the full deduplication in the graph that you have seen, which is to say, if the same file is present in 1,000 projects, we store it only once. So we removed that, the redundancy, but we decided to stop at the file level. So if a file is different from another file by just 1 bit, we store that copy, which is, as you say, pretty inefficient, because especially the auto version are just a change a line in a column. But we didn't have the confidence of being able to do this properly, and so we wanted to have all the data on one side. Today, one of the sub-projects, which is part of Code Commons, is work with a colleague from PISA, who is an expert in data compression, data search engine, etc. We have been performing quite a lot of experiments on compressing the data And we are confident we can actually remove a lot of that redundancy. If you are familiar with what the modern version control system do, like for example Git, Git uses something called the Git bugs. Git bugs are the compressed version of the file, the version that removes the redundancy. But it is really based on the fact that you have the knowledge of the history of a particular project. Since we share the history of the project across thousands of projects, we cannot use that approach exactly. So we are using another approach. In a second, it's just you cluster the files by the file name. So we tie locally sensitive hashing. Other things, but what works better is just the file name. So apparently manual typing is better than locally sensitive hashing. You put together the files that have the same name and in similar size, then you run the standard compressor on top of this with a bold window, and you get incredible results in compression. So we are trying to work into that direction, but I do not want to move to that until I'm fully sure that I'm not going to lose the content.
How the software work with licenses specifically, because I imagine that would be a lot of bureaucracy, especially because I imagine that GitHub and GitLab have different licensing models, and sometimes you may not copy the code exactly, or may copy but not of business, and then you need to replicate that on software types. How does that work?
Another thing, so many things. You have the best audience I get in up to now, so I have to say. Very, very good question. So it is not just a technical challenge, it is also a legal and social challenge to build such a thing, which is something usually do not want to do, because technical problems are easy to solve by legal and human law. Okay, but we collect everything which is publicly available, which means that inside the archive you will find tons of things that have no license, that have maybe semi-proprietary license, to say you can only use it for research or whatever. But the point is that since we are building this as an archive, we believe that being an archive is a mission like the Internet Archive that allows us to keep a copy. And if you look at the condition of use for software, it clearly states that it's up to you, when you come to the archive and get a copy of the content, to check what is that you can do. Okay, so you need to do it your own due diligence to see what the license says, etc. But then about the issue of what are the terms used, for example, GitHub, etc. In 2019, we wrote an agreement, we signed an agreement with GitHub, because GitHub wanted to have the software on GitHub actually archived for the long term. So we have an agreement with them that actually obliges us to make a copy. If you remember, they had this beautiful publicity stand of the GitHub Arctic Vault. Did you hear about this kind of thing? So the idea they take the head of the most popular projects, they print it on a celluloid thing with a 3D or whatever, I don't remember. They put it in a box, and this box is put in the Arctic, in a vault with a nice little flag, and this is French, or this is German, etc. Because this will be preserved for 10,000 years. But I don't know, I mean, somebody 10,000 years come here, you find the software from 10,000 years before. I don't know. So that, I mean, part of the game is that, which is a nice publicity stunt, and they took journalists with a helicopter to go to the Arctic world. Very nice part. I'm not sure if it is very useful. But another part of the agreement was that we archive everything that is on GitHub. And so you see, the agreement with GitHub is there. The question of the license is actually basically up to you to check what is there. And what we are trying to do inside Coconos is to run a license scanner at gigantic scale. I mean, a license scanner on tens of billions of files. It is not something that you can do without access to large supercomputers to massively do this. But we try to do this to provide metadata which is available for people who come and say what is the license of this object. Knowing that we only store facts and not opinions, so you will never see on software just saying something saying this software is under JPL license. You will see statement like running these license protection tools on this software, we say it is GPL. And this is a fact. You see the difference between it. Okay.
Thank you for this motivating talk. It's very intriguing in some parts because you mentioned blockchain, that blockchain is in your infrastructure, but you mentioned also centralized. So how do you integrate these two views, point of views in your infrastructure?
Yeah. Okay. Again, when you think about blockchains, I mean, the usual terminology that we use, also in the media they use, you always think about decentralized. But there is nothing about decentralization in the blockchain technology. Okay? Decentralization is one particular application. Actually, yes, we had many mirrors. The mirrors had the same blockchain. So since we have these identifiers which are intrinsic in the code, we are sure that what you find there is the same as what we have here. In that sense, you have multiple copies of the same blockchain are decentralized. That's going back to your question about distributed versus centralized replicated. So we try to actually make a compromise this particular way.
Now, secondly on this, what's the role of metadata standards and ontologies in the way, because documentation has always been a challenge with software developers.
Thanks a lot. Another very good question. Unfortunately, again, in the demo Paris Cité one time, 7 years ago, when I managed to hire the only lady I had in the moment in my team, which is very young lady, she was working on metadata and ontologies for software. So the first work was to do a state of the art, and she came up with 50 ontologies for describing software. So there are probably more ontologies than users of the ontologies around. But then there was a meta ontology, which is called code meta, which is basically a correspondence table between the different ontologies, and you have a concept. And so we ended up using this code meta thing. Although the archive, it is a code meta thing that is used to generate a citation. So there is a community working around that kind of standard. It's not an ISO standard yet, but it's a de facto standard to provide basic description of the software, typically the programming language, the license, the infrastructure on which it can run, the author, the contributors, the funding, etc., etc., which is super useful for us in academia to actually, for example, generate reports on the production of software, etc., etc. But we want to go much farther than that. And this again, in this Code Commons project we're working on, we would like to have information about the licenses, information about the issues, about the merge request, about the connection with application, etc. And so the data model is becoming much bigger.
How often you have to make changes in the adapters? Like, I think that dealing with third-party like APIs to get the data could be a little tricky. And you have some help from GitHub and GitLab to do so?
No, we don't have help. Yes, well, let's say, what can I do? I mean, how often do we need to make changes? Not that often, luckily, because if they change API, this creates a mess for everybody. For example, one of the parts of the agreement with GitHub is that GitHub has created a specific extra piece of metadata which is available only for us. If you go to the event field, for example, you can list, in a couple of days, you can list all the projects which are on GitHub. But the standard answer misses the key information, which is the date of last modification of a project. And you see, for us, this is very important, because if I get the list of 300 million projects, I do not know what changed or not, I need to go through the 300 million, which is disaster. So we ask them, they added this, and they maintain this only for us. Every now and then it disappears, because somebody made a modification, so we need to go back and say, okay, can you fix it enough? Okay, but this is the particular thing that they did with us for the moment. The challenge is to actually add all the other things, for example, but I don't remember the name of the other person. There are a bunch of things which are still missing in the list. But again, writing an adapter today is not difficult at all. There is a lot of documentation. If there is something that is interesting for you, which is not there, just feel free to come and knock on the door, and write something really integrated.
So suppose you have an open source code that is stored on GitHub, and then you archive it, and so there are a lot of files there. You archive it, you give a hash identifier, and then a day later, someone publishes a new file on the same repository, and then the archive is run again. What is it that is kept on the archive? The whole project, or just the modification, and then you link these things together?
Another very, very good question. So basically, let's say how to, the property of this bucket hash is that actually, if I rerun the archive at the part where you changed only one file, the only new thing that we added to the graph is a new project and a bunch of modified directories up to the root that point to it, but not the rest. The typical thing that you find in functional data structure, it's exactly the same way. But the other interesting point is that whenever we archive a project which is under a version control system, not something which is just in a package manager, we archive all the version history, which means that if somebody changes version history, for example, git rebase, etc., we see it, because when we come back, we re-archive the other history, and so we have a history of histories. And this is particularly interesting for cybersecurity, because the typical thing bad guys do today is to come in, add in the system something bad, and then rewrite the history to hide who wrote the thing. So if you look at the rewriting of histories, you have interesting things to say. And how do you look at rewriting history? You download your graph and you run your analysis. This is the incredible new thing, the power that you have. You can run this analysis yourself in a reasonably small amount of time. Maybe time out, they stop.
Maybe one last question. So, Professor Di Cosmo, thank you very much for your talk.
Thank you.
So this is Professor Patrick Valturiez.
This was a great talk. So I just want to say just 2 words. Who am I? So I've been working with Brazil for a long time. So I'm the director of the Inria Brazil Strategic Partnership. So this conference and the set of conferences, because yesterday we were at the RNCC and on Monday at PUC, is in this context of Inria Brazil. So what is Inria Brazil? 2 words. Just a way to foster collaborations between Inria teams, like for example this one, or my team. So for example, Marta, with here, Shanice, we have collaboration, and teams in Brazil. So the hub in Brazil is LNCC, namely Frédéric Valentin, that you may know. But so I'm here to foster projects between India and Brazil. And what is evidence for me today here is that because there are a lot of engineering, software engineering issues in software heritage, so if there are groups of people who want to collaborate with people at Inria, they can let us know, and we'll be pleased to. We have tools. I'm not going to explain the programs and whatever, but money is not the issue. You can always find money. The thing is, we need to build, bottom-up big teams. Okay, thank you very much, and thank you again. And thank you, Janice, for the organization.
You are always welcome. Bom, pessoal, muito obrigada a todos os presentes. Então, boa tarde a todos e todas. Obrigada, até a próxima. Thank you. It was very interesting.